Greetings and welcome back. Today we're going to learn about compilers and a few other things associated with it like linkers and optimization. I'm going to try to keep the content of this video pretty generic so that way it's not applicable to just AVR microcontrollers, but you could also take this knowledge and use it for STM microcontrollers as well. Eventually our goal is to program in STM8, so I don't want to spend too much time learning just AVR and then having to throw that all away and relearn it again all for just STM microcontrollers. So let's get started. The main purpose of a compiler is to take code that humans write and turn it into something that the processor knows how to execute. In this case, we can use this example of I equals I plus 1, and our goal is to convert it into machine code so that way our microcontroller can do something with that. It's very common to store the machine code in a .hex file so that way it's easy for a human to read, but also for the programmer to transfer over to your microcontroller. For something even as simple as I equals I plus 1, there's many different ways that you could translate that into machine code. And one example of that is to take I and load it from memory, which is this first section. We're pulling it out of RAM memory and putting it into the processor. Once it's in the processor, we can increment that value by 1, so we add 1 to it, and then we take that value and store it back into memory. If you were to write this in AVR assembly, this is what it would look like on the right. We're telling this to load some data from address in RAM memory 22 into something called register 24. Then we do this add word instruction where we add a hard-coded 1 to whatever is in register 24, and then we store back whatever was in register 24 into memory address 22. My goal for this video is not to teach you how to write AVR assembly code. However, I do want to focus on these 3 instructions because it's really simple and we'll convert this over to machine code to have a better understanding of what compilers are doing behind the scenes. And this would be one way to execute this I equals I plus 1 instruction in C. After you've got that in assembly and you've figured out what instructions you want to do, it's extremely easy to translate that into machine code, which are the ones and zeros that make your microcontroller tick. The program that converts assembly code into machine code is called an assembler, and this is something that you can really do by hand. What we're going to do here is we're going to take this add IW instruction and we're going to convert this over into its machine code, which is a result of 0196, and we're going to do this by hand by referencing the AVR datasheet. This datasheet is documented online. If you search for AVR instruction set, it gives you a list of all of the assembly commands that AVR-based microcontrollers are capable of understanding. So in here we have this add IW, which is add immediate to word, and that means that we are going to add a hard-coded value, which in our case is going to be the number 1, to a word. And for simplicity, a word is just some number being stored in a register. Now we can look at the details on how this ADIW instruction works, and there are some limitations to it. Firstly, we can add any immediate value between 0 and 63, so we couldn't add any large numbers, but if we're just trying to increase a value by 1, we could use this. We also can only operate this on 4 register pairs, so that is registers 24, 26, 28, and 30. For this case, let's assume that we chose register 24, and that's where our value I was currently loaded. Reminder, this is just to add 1 to that. So we're going to say that 24 already has our value I, and our goal is to add 1 to that. So what we can do is we can take this little data sheet here, and we can read what the opcode is, or the command to execute it. And we can see that it always begins with 1001 0110, and that's called the opcode, which is right here. That means we are executing an add immediate to word instruction. After that, we have some parts that we can put in whatever we want, and it's split into KK, DD, KK, KK. So we know that we want to use register 24, which means that we're going to use a D value of 0, and that's because there's 2 Ds here, 2-bit number, which means that we can represent any number between 0 and 3, and those are what translate into what is shown here. So we're going to use 24, which means that we're going to set our D value equal to 0, which is 0, 0 when you use a 2-bit number. Finally, we have the number K, which is the number that we want to add into that register. So in our case, we want to add 1, and 1 in binary is just all zeros followed by a 1. So if we plug our information back into this formula that we've got here, we end up with this number at the bottom. The green section is the opcode. We have the blue section, which is the number that we want to add, and it's kind of split up here, which is a little annoying, but 0, 0 finished over here, 0, 0, 0, 1. And then our register is specified in red as these 2 zeros, which will be register 24. And this number here, converted into hex, is 0x9601. Just a reminder, most calculator apps have a programmer mode. So Windows has one for sure, Mac has one for sure. And the way that you switch this in Mac is to go to the View dropdown and say Programmer Mode, which now gives us options to see all these different things. We can set this to hexadecimal here, punch in our binary number, which is 10010110, then all zeros and a 1, and we end up with our 9601, which matches up appropriately with this. Okay, cool. So now we know how to take that add immediate to word instruction, reference the data sheet, and convert that into the ones and zeros ourselves in order to calculate the machine code for it. So if you were to look at this, which is our second instruction in this set, it translates over here to 0196. And you might realize that that's kind of backwards-ish from what we were looking at before. And that's because AVR uses little endian format, which means that we do the little byte first. So when we chop it up into bytes, which is every 2 digits in hexadecimal, we kind of write those in reverse. So 9601 becomes 0196. Any assembly code can be directly translated into machine code, and vice versa. Machine code could be reverse compiled or reverse assembled into the assembly. Now, modern day assemblers do give you a lot of extra features that allow to save some time when you're writing assembly code, but for the sake of this video, I'm just going to pretend that machine code and assembly are identical. There's many different ways that you could turn I equals I plus 1 into assembly code, or therefore machine code. And the example that I gave here isn't really the best way of doing it. There is a better way of doing that, but that's what sets apart a good compiler from a bad compiler. And sometimes this is a make or break between how quick your program is able to run and how compact your program is when it's compiled. One such compiler for turning C code into AVR-based instruction set is something called AVR-GCC. And this is the compiler that comes bundled up with Arduino. So let's take a look at how Arduino compiles your code. Here we have our infamous blink example. So let's push this onto an Arduino Uno and see what's happening behind the scenes. So in order to do that, I need to go to my tools and select my board. This is going to go to an Arduino Genuino Uno. Port doesn't matter since I'm using a USB programmer. I have to specify that here is USB Tiny ISP, which is all set. And now that we're done with that, we can go to the sketch dropdown and hit upload using programmer. And this will compile the sketch, which we can see here, and then upload it. Now I have verbose mode turned on, which is in the preferences for Arduino, and I'm going to scroll all the way up to the top. We can see that there's a lot of calls to this program called AVR-GCC, and it even tells us where it lives. On my Mac, that's under the Applications folder, Arduino.app, Contents, Java, Hardware, Tools, AVR, Bin, and so forth. This will be in a different location if you're running Windows or Linux as well. And then everything that comes after it is all of the arguments that tells the compiler how to compile your code. In my previous video, we took advantage that AVRDUDE came bundled with Arduino, but for this video, I'm going to show you what it's like if you were to completely ditch Arduino and we'll install it manually. We could use the AVR-GCC that came with Arduino, and we could just reference it by running it from the folder that it lives in, but I'm going to install it as if I didn't have Arduino. So these are the instructions on how you should be able to install AVR-GCC. I'm running a Mac, so I was able to test this out and know that everything works here. I did a quick Google search, and this is what it looks like you need to do for Linux and Windows. You have to download a .exe file. I haven't tested these, so if you find out that these do or don't work, please let me know in the comments and I'll update the video description, but I did test the Mac install. As a reminder, AVR-GCC is a compiler to compile AVR code. My goal with this video series is to not specifically focus on AVR, but rather teach you the basics of compilers so that way you can apply it to other things. So instead of just jumping into a how to use AVR-GCC, I'm going to kind of go into how to figure it out for yourself. In order to learn how to run a program, there's a thing called man pages. And the way that you can access that on a Mac or on Linux is to open up a terminal and type in man and then the name of the program, which is AVR-GCC. And it will give you a giant dump of all of the documentation on how to run this. Let's take a peek at how to find out all of the information about AVR-GCC. So in a terminal on Mac or Linux, you type in man AVR-GCC and it will give us the manual for this. And this is a massive, massive, massive data sheet. This just goes on and on and on. One little tip that makes it really handy to search data sheets is to take advantage of the commands that you can do. I don't know if this editor is Vim itself, but it's very similar. You've got this little colon in the bottom left-hand corner where you can execute commands. If you type in / and then what you want to search for, so like MMCU, and you hit enter, it will search the entire document for MMCU, and it shows up here. And if you want to jump to the next entry, just hit N on your keyboard. N, 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 and it will keep jumping between all of these. AVR-GCC works for more than just AVR-based microcontrollers. You can see that there's also some ARM-based options, and we've got Blackfin and C6X, but the part that we really care about is AVR, and it gives us a little description of some of the flags that you can use when you're compiling AVR code. The one that we care about mostly is this first one, which is -mmcu. Why do we need to tell the compiler which microcontroller we're using? Well, if you look at an example of one of the instructions that's documented in the instruction set for AVR, they have this little part here that says this instruction is not available in all devices. Refer to the device-specific instruction set summary. And if you look further down in the datasheet, it will tell you which devices have support for which instructions. So not all instructions are supported by all microcontrollers. And because of that, it's important that we tell the compiler which instructions it's allowed to use and which ones it's not allowed to use. Because of this, there is a giant list of all supported microcontrollers, and if you look far enough down in the manual pages, you will find the ATMEGA328 family. So we've got the 328P as well as the 328PB, and all of these fall under the category of AVR5, which is the AVR5 instruction set. If we don't tell the compiler which instruction set to use, it will default to AVR2. With just this little bits of knowledge, we are able to run a bare bones compile command. So what we need to do is we need to say the name of the program, which is AVR-GCC. We need to tell it which microcontroller we're using so the compiler knows which instruction sets it's allowed to use. And finally, we need to tell it our .c source file here. So if we have a program called dummy.c and we're trying to compile it for an ATMEGA328P, we just need to do AVR-GCC, specify the -mmcu flag of ATMEGA328P, or we could hardcode in AVR5 here, and then our file. If we don't specify any other flags, the compiler is just going to use some defaults for us. And one of those defaults is what to save the output file as. So if we don't tell it specifically what we want the file name to be saved as using the -o flag, then it will save it as a file called a.out. Now let's reference the code that we wrote in the first two videos here, which is a very simple blink example that we tried to avoid using any Arduino code possible. So I'm going to open this up in Vim dummy.c, and we're going to essentially copy this and then work from there. So we've got our define statements, define, and now we have to call port B. So I'm going to call this port B. I did it Mitch port B before just so I wasn't copying any Arduino slang. We're going to do byte star 0x25 here, and we're going to do that same thing here, except this one's going to be called DDRB, and this one is byte 24. And there was one thing that I forgot to add in that screenshot. We had to put this volatile keyword in there, which is kind of not necessary right now, but we're going to do it anyway. That tells the compiler to not try to optimize this code out. Next we have this void setup, which is what gets called first in Arduino, where we set the DDRB equal to 32. We're going to come down to our loop, void loop. We're going to do our port B equals 32. We're going to do a for loop here. For long I equals 0. I is less than some big number just to give us a long delay. 1, 1, 2, 3, 1, 2, 3. That should be long enough. I++. And here we're just doing some dummy code to execute. We'll just repeat the same code that we had before, which is port B equals 32. We're going to repeat that exact same thing for turning the light off. So port B equals 0, which will turn off all of the ports on port B, all the pins on port B. Do another for loop, long I equals 0. I is less than 100,000, I++, and port B equals 0. So that will just begin by turning our pin on, which is pin 13, and doing that over and over again 100,000 times, and then turning it off over and over again 100,000 times in loop. So this is where we left off last time. Let's see what happens when we try to compile this. Now to compile, we said that we wanted to use AVR-GCC. We want to specify our microcontroller, which is -mmcu equals ATMEGA328, and P doesn't really matter all that much for this. And now we want to say our input file, which is dummy.c, and you can hit tab to autocomplete. And if we try to compile this, it's going to throw all sorts of errors. And the first one that stands out is this byte pointer. And that's because it doesn't understand what a byte is. And it has a few basic data types that it does understand. So what we're going to do instead of a byte, we'll jump back into our Vim, is instead of using byte, we're going to use a character. Now a character goes from -128 up to +127. So what we're going to do here is not just use a regular character because it's signed, we're going to use an unsigned. And an unsigned character then goes from 0 up to 255, which is therefore a byte. We're going to do that here as well. Unsigned character pointer. And let's try to compile this code again. We're going to hit up twice to run our code, and now it's yelling at us here, saying an undefined reference to main. Well, what this means is the structure of our code doesn't work. So Arduino uses setup and loop in order to run, but that's not anywhere in C. The way that C works is it expects there to be a very special method called main, and it expects it to be an int main and then with no arguments, or you can pass in some arguments if you want. And this is what is normally going to run. So we're going to use this instead of our setup method here. So I'm just going to get rid of this, and we're going to go paste it up here. And we're going to get rid of our setup line altogether. What we're going to do here is we're going to put our loop code in here. We're going to say while 1, which is an infinite loop. We're going to loop over and over again forever. And I'm going to go into visual block mode here, yank all this code, paste it back over here, and tab things over a little bit so it looks cleaner. And get rid of our extra line that we've got here. So now this is what our code looks like. Everything lives inside of this main method. We've got our while loop, which is going to be our infinite loop to keep turning things on and off, and we should be good to go. Let's try and compile this one more time. And everything seems to work. And if I type in ls, we can see everything that's in here. And we've got our a.out, which is our binary file. Now if we want to peek into the contents of this a.out, we could type in hexdump, which will show us the entire binary contents in hexadecimal for a.out. This is what it looks like. It's extremely long. There's a lot of stuff going on in here. And this is the compiled code. We have this a.out file, which is now technically machine code, but the question is, can we just upload that to our microcontroller? I don't actually know the answer to that. I do know that the standard is that everyone converts that file into a .hex file, and then you upload that instead. In order to translate that machine code into a .hex file, there's a program that comes bundled up with AVR-GCC, and that's called AVR-OBJ-copy. So if you installed AVR-GCC, you should already have this command on here. And if you just type this into a command prompt blank and you just type in AVR-OBJ-copy, it's going to say, hey, you forgot a few things. Maybe you should try some of these commands. And this gives us a bunch of different options. And the ones that we care about are this -O flag and the -J flag. -O is what we're going to specify our output target as. So we need to specify that we want our format to be a .hex file. This -J has something to do with the contents of what a compiled file looks like. So this is what a bare bones command looks like. We type in AVR object copy, which is our program name. We have to specify the output format, and that would be done with this -O, capital O, ihex, and then we specify the file that we want to read from, which is our a.out file, which was generated from our compiled code, and our output file would become a.hex. The reason that we're using this ihex file is because that was one of the formats that AVRDUDE supports as an input file. And I'm sure that you can find some other output formats that this AVR object copy supports and AVRDUDE supports, but hexadecimal seems to be the most common, so we're going to go with that. If you were to break down the contents of that a.out file, it would fall into something that looks similar to this. At the very beginning, we have this section called the text section, then we have the data section, then we have something called the stack, we've got some free empty space and a heap. And this is what your program generally looks like. However, the only parts that we really care about for our microcontroller is the text section, and that is where all of our code lives, and then this data section. And data is just where it kind of dumps a bunch of memory. And that's usually how it's organized, is two separate sections. It could be interleaved, but it's almost always done like this. We don't really care about our stack, free space, or heap, so we can tell AVR object copy to only use this text and data, which will make our hex file much, much smaller, which then allows us to put more data on our microcontroller by using this -j flag. So if we want to just use the .text and .data, we do -j.text and -j.data, and it will ignore everything else. So this is kind of the recommended minimal format of this command, which would be then AVR object copy, our output format as Intel hex, -j text, -j.data, and our input file is a.out, and our output format is our output file is a.hex. So let's give this a shot. We've got our files here. We have a.out and then our original source code dummy.c, and we're going to do AVR object copy, obj copy, and we want to specify the output format, capital O I hex for Intel hex format. We want to do just the .text and just the .data section from that. Our input file is a.out, and our output file, we're going to call it a.hex. So after we're done with that, it seems to run just fine. We can do cat to just show us the data. This will dump the hex file that we've got, a.hex, tab to complete. And this is what it looks like. So this is the Intel hex format, and this is our Blink example after it's been compiled and then translated into Intel hex format. And this is something that AVRDUDE is able to read. I've got my cheat sheet from my previous video on how to run AVRDUDE. One of the things that we do need to look up though is where this AVRDUDE.conf file is. There's one that's bundled with Arduino, but since I'm trying to distance myself from the whole Arduino IDE, we need to find that on our own. So I'm just going to open up a file search here, and I'm just going to search for AVRDUDE.conf, which is the name of the file. Should show up a couple of results because some are Arduino. Let's see, this is part of Mighty Core, which is Arduino. I don't want to use that one. It looks like this is also Arduino, which there we go. So this is the one that comes pre-installed. This is the default configuration file that comes when you install AVRDUDE on your computer on your own. So I'm going to copy this as a path, which if you hold the Option key on a Mac or Alt on Windows, you can copy it as a path name. So now I've got that in my clipboard, and let's actually run this command. So AVRDUDE -C for our path, and I'm just going to paste that in there. There's our configuration file. Yeah, we'll do -V for verbose so we can see extra stuff. The chip, our target chip, is -P ATMEGA328P. Our programmer is -C USB tiny. Now if you're using an Arduino as ISP, you have to specify a couple of other commands in here, which are covered in my other video. And now the data dump, what we actually want. -U is for a user program. Our goal is to flash something. We're going to flash, we're going to specifically write data. And now the path to our sketch. And since we're in the folder that we want, we just want to do our a.hex file. So I can run that, we can see a lot of stuff happens, and let's check if that did anything. All right, we can see that our LED is blinking. It's blinking very slow, but that's just because we chose an arbitrary amount of time to wait. But it looks like our code compiled, copied, and uploaded to our microcontroller. Now you know the basics of how to compile code that an AVR microcontroller can understand. In order to write practical code, there's still a few other things that you need to learn, specifically linkers and optimizations. That's going to help you write larger code, maybe tie in some libraries, and also make sure that your code size stays tiny enough so that way you can pack more onto your microcontroller. Unfortunately, I ran out of time for this video because it took a little bit longer to cover the intro than it was expected to, but I will push everything else into another video, and I'll see you next time.